Okay, so yeah, here is an outline of what the next 90 minutes are going to look like according to our plan. So at the beginning, I'll be talking about those quantum computing fundamentals. And then after that, I'm going to pass it off to Amanda, who's going to talk about one phase of quantum compilation called quantum circuit optimization. And then I'll be talking about another phase called the qubit mapping and routing. And then finally, Amanda is going to close us with like a fun practical demo of our tool, which is software that implements both of these compiler passes. That's the plan. First up, these quantum computing fundamentals. So if you look at a classical bit, you have two states, 0 and 1, and the qubit is the quantum analog of the bit, and it similarly has two analogous states. This that we denote like this, we call this one ket 0 and the bottom one ket 1. But the interesting thing that separates quantum computing is that not only can we be at these two polar states 0 and 1, we can also be anywhere on the surface of this sphere of states that are between them. So for example, another valid qubit state is this orange vector here that is sort of halfway between 0 and 1. That's what separates quantum computing. More specifically, so I mentioned that the state of a qubit is a point on a sphere, and we can that point is sort of it's a 2D vector, just like latitude and longitude. They're a 2D vector that represents your position on the sphere, that's the Earth. And we write these vectors like this. So we have the basis vectors, ket 0 and 1, like I said before. Those are our analogs of the classical states 0 and 1. And then we have these complex coefficients in front of them, alpha and beta. So a given quantum state is just some linear combination of ket 0 and ket 1. Okay, so the thing that complicates using our qubits is that quantum mechanics does not allow us to know exactly what alpha and beta are here. We can't know precisely what state that will in. Instead, when we apply a measurement, we will get one of two outcomes. We get ket 0 with probability alpha, the norm of alpha squared, and ket 1 with probability norm of beta squared. So because of these are the probabilities of two outcomes, we get this implication that these two probability, they have to sum to 1 in order to actually be a valid probability. So this is what measurement does. It gives us either 0 or 1 with probability that is associated with the coefficient in front of that in our state. Okay, in order to transform the state, we apply gates. So one gate that is pretty easy to understand is the X gate. This is like the quantum analog of the NOT in classical computing. So the classical NOT, right, it sends 0 to 1 and 1 to 0. And the quantum NOT is like it's a generalization of that. It sends alpha ket 0 plus beta ket 1 to beta ket 0 plus alpha ket 1. So you can verify on 0 and 1 that behaves as we expect, and then we sort of linearly generalize that. And this we can think about as a matrix. So if you look at this matrix up here and then you apply it to the vector alpha beta, you'll notice this is like the swapping matrix. So if you apply it, then it takes alpha beta to beta alpha. Okay. So that was pretty classical, but we can also do very different things in quantum computing. So the Hadamard gate is an example of an intrinsically quantum operation. So this takes one of our basis vectors, 0 or 1, and takes it to an equal superposition of 0 and 1. So here's the matrix corresponding to this Hadamard operation, and here's its behavior. So it takes ket 0 to this equal sum of 0 and 1. So you can notice that we have the same coefficient out in front, this 1 over square root of 2. You can verify that if you square that, you get 1/2. So if you add them together, you get 1. So it's sort of this normalized equal probability of 0 and 1. And then if you look at the action of Hadamard on the ket 1 state, once again, we're going to get the same probabilities. It's just that one of these coefficients has a negative sign in front of it. So we have 1 over square root of 2 minus 1 over square root of 2. So when you do the squaring, that negative goes away. So the probabilities are the same, but there's this difference in phase between the 0 and the 1 state. That's the Hadamard gate. And so just to summarize this part about single qubit gates, once again, a single qubit gate is, on one hand, it's a 2x2 matrix, and in particular, it has to be a unitary matrix in order to preserve the norm of these states so that we're always getting probabilities out when we do our measurements. But on the other hand, we can think about it as rotations on this sphere representing the state. So the state of a particular qubit is a point on this sphere. So a gate takes a point to another point. And it has to be like, because it's a unitary matrix, if you know some linear algebra, you know that it has to be like this rigid transformation that we can think of as a rotation. So for example, the x gate, right, it flips 0 over to 1. So that sort of rotation. And then the Hadamard is taking us to this intermediate state I talked about before. It takes 0 to this halfway point between 0 and 1. You can visualize how it's orthogonal to the 0 1 axis. Any questions at this point about single qubit gates, measurement, that sort of thing? We have seen some presentation of quantum computing. You might have seen these things before. So, okay, so we can extend this to systems with more than one qubit. Now we have a 4-dimensional vector space with some these analogous basis vectors of all the combinations of 0 and 1. And then once again, we have operations that can act upon our qubits. So here, one of the most famous 2-qubit gates is called the controlled NOT or C NOT or CX gate. And this basically, it's a kind of like the quantum analog of the XOR operation. So it's flipping the second qubit conditional on the first qubit. So in other words, it's taking the XOR of the first qubit and placing that, and it's taking the XOR of the 2 qubits and placing that in the second register. So if the first one is 0, then it does nothing to the second one. If the first one is 1, then it flips the second one. And you use linearity to observe how it behaves on the superposition states. Okay, so quantum circuits are just the composition of gates. And so we have these 2 different representations of them. So we have like this assembly-like language where it's like, okay, first apply the Hadamard, then apply the C naught as the sequence of lines. Or on the other hand, you sometimes see these sorts of diagrams. So each of these horizontal wires is representing a qubit, and then we read sort of time moving from left to right. These are 2 representations of the same computation, which is again also just a matrix, right? Because if we apply this Hadamard and then the C naught, they each have their associated matrices, and then the composition is multiplying the matrices plus some additional tensor operations to make the same size quantum circuits. And this is not just a theoretical construction anymore. You can actually run quantum circuits on real quantum hardware today for free. If you're sign up for the account. So this is like some Python code. The details are not important, but just showing how you actually do this. Yeah, go ahead.
Does it still take like months, or is it much faster now?
It's really about how long you're sitting in the queue. Because the actual operation is I haven't tried it recently. I would expect it not to take months, maybe hours. So like the actual quantum computation of this would be like, microseconds, but it's the waiting in line for the access. But now IBM has lots of devices you can access, so it depends on and you can always pay money to jump the queue, these sorts of things. But this is the Python code for interacting with IBM's cloud service. You have some boring cloud authentication stuff that you would need for any such service, and then constructing your circuit. You can they have this Python package where we can construct the circuit we had before with the Hadamard and the C naught gate, abbreviated CX, and then we pick some device to run it on, and then you can sort of compile your circuit for that device and then get back the results. So this is something you can actually do. And these devices are what we call noisy intermediate scale quantum devices. So that's abbreviated as NISQ. And in this NISQ regime, we have hundreds of qubits, which is not enough to do error correction protocols, which I'll talk about in a little bit. So instead, we rely on sort of smaller scale error mitigation tricks. And we have noisy here. Each operation is very noisy, which means there's some probability of error associated with it. And so what that means is that we have to sample many runs of our circuit in order to get like a good sense of what probability distribution we would actually expect. So like there's a noisy probability distribution, we have to take lots of samples. And so what this means is that people are interested in using these NISQ devices for real problems, but they have to kind of be approximate algorithms. So there's this thing called QAOA, quantum approximate optimization algorithm, which is an example of that, where it's basically a framework for solving like approximating global optimum to optimization problem. So you don't actually care about getting the true optimum, but it's something where you are okay with something that approximates the global optimum. That's an algorithm that you can use for it. So this is sort of the applications, what the flavor of applications that NIST devices are used for. But we're moving towards a world of quantum error correction. So this is what you need in order to do those really exciting applications that you might have heard, like Shor's algorithm, like simulating molecules for drug discovery. All of these long-term applications of quantum computers will be run on error-corrected quantum computers, where the idea is, intuitive. You encode a logical qubit using several physical qubits. So that redundancy kind of reduces your error, and the larger you scale your logical qubit, the lower your error rate goes. And in particular, one encoding scheme that's very promising right now is something called a surface code. And here's like a depiction of a surface code qubit from Google's blog, and it sort of is a surface, right? It's like a two-dimensional patch. Okay, and we have seen surface codes in hardware. So just a couple of years ago, we saw kind of the first experimental demonstrations of the surface code protocol that I showed you there. And then just last year, we had this really exciting experiment that demonstrates this principle of quantum error correction that I mentioned, that as you scale your logical qubit, your error rate goes down. So these at Google, they basically constructed a small logical qubit and then a big one, and they observed that the big one actually reduced the error rate. So that is promising because it shows the scaling principle actually can work in real life. Okay, so since we have these devices coming, let's talk now about the software that you need to interact with quantum computers. On one hand, you have a high-level program, something like this, that's like, okay, this is what I'd like to, this is the algorithm that I'd like to execute. So given something like this, we need to convert it into one of our quantum circuits. So that might look something like this. But this quantum circuit has these additional operations that are kind of not actually natively executable on our device. So we need to decompose them into the native basis gate set of our device. So particular hardware can only execute some limited number of operations, and so we need to decompose other things into them. And so that might look something like this, where here we're using some shorthand to denote this sequence of gates that's very common. But here we have now a circuit in the native basis gate set. But still, because individual operations are noisy and other concerns, we want to minimize the size of the circuit that we actually execute. So this is where a quantum circuit optimizer comes in, where we're trying to optimize the circuit with respect to some cost functions. That might be something like the number of gates total, the number of a particular type of gate, or something like that. And so quantum circuit optimizer takes that circuit and produces one that looks like this, that's semantically equivalent, but better with respect to our cost function. And then finally, we have some physical connectivity constraints on our device that tell us about what types of gates, what pairs of qubits we can perform gates between, things like that. And this is solved by the mapping and routing phase, which produces a circuit that we can actually execute on our device. So now I'm going to hand it over to Amanda, who's going to talk about this middle phase of circuit optimization. But before I do that, are there any questions about this? Yeah, go ahead.
Is like copying a qubit, if you want to like get it from like one register to a different one, like that's something that's easy to do, or is that different?
Yeah, so direct kind of copying of an arbitrary state is something that you can't do because of quantum mechanics. There's something called the no cloning theorem. So you have to do other things in order to move your quantum data around that I'll talk about a little bit later, but it's not simple. Yeah, good question.
Are you going to talk about quantum oracles?
About oracles? Not very much in this talk, no. So we're mostly going to be talking about sort of given a particular circuit that you'd like to execute with sort of all of that kind of flattened out already into the actual operations you'd like to implement. Yeah.
Can you go back a couple of slides to the scaling of qubits?
Yeah.
It said 1 hour at a time. What exactly do you mean by 1 hour at a time, 2 hours at a time?
Yeah, so basically the way that error correction works is you're repeatedly applying this cycle protocol, and the larger your logical qubit is, the more errors you can correct in a single cycle. So, and that has to do basically with, if you're familiar with coding theory, the code distance of this code is like the side length of the square. So this has a code distance of 3, which means that we can correct up to 1 error and detect up to 2 errors. So that's what this is saying, is like this larger qubit can detect or can correct 2 errors per error correction cycle. I see. Yeah. You have a follow-up?
No.
Okay, go ahead.
Do you guys ever work on these weird what are they called, like quantum adiabatic computation? There's like one company that
Like
at one point made fairly ridiculous claims about their qubit. And it turned out they do something very different than like what we typically think.
yeah, so
Yeah.
we are focusing on the systems where it's like a gate model, like what we described, where you can sort of apply gates. That the quantum annealing stuff is like slightly different. So yeah, they don't quite have the full power of this model of quantum computation. But which is why they're able to sort of demonstrate some things earlier, because it's not quite as powerful of a computation. So, but we won't be talking about that.
Okay.
Any other questions? And I'll hand it over to.
It's not universal, right?
No, it's not.
Yeah.
There.
Great. Okay, yeah. So in this part of the tutorial, I'm going to be talking about the phase of the optimizer that is operating over the circuit in this native baseless gate set. So first we need to define what that is. It's pretty simple if you know what like ISA is. This is just like an ISA for a quantum computer. So for a given device, for example, maybe the IBM device, you can execute these gates natively. And so this one is like the RZ rotation around the z-axis by some angle theta, and the other ones, that's okay. You don't need to. They are. But these form a set, and it's important that the set is universal so that you can actually perform quantum computation, unlike I think that you're mentioning. And what it means is that you're able to approximate any computation you would like to do up to some arbitrary precision. And so some objectives that you might have when you're optimizing a quantum circuit, like Abtin mentioned briefly, is just to like reduce the gate count, because each of these gates is going to have some probability of failure. And so when you have enough of them, then you're going to build up so much noise that when you measure your qubits, it's indistinguishable from just random noise. So in the NIST regime, a very natural optimization objective is to just reduce the total gate count. But also you might notice that the probability of failure for these 2 qubit gates is an order of magnitude higher than for the single qubit ones. So it might be more worthwhile to focus on reducing 2 qubit gates instead. And then when we shift into the regime where we have error correction, the objective changes a little bit, because now we have these gates called T gates, which are these z-axis rotations by a particular angle, and they're going to be expensive to perform fault tolerantly. And so your optimization objective is now a little bit mixed. It's like, I'd like to prioritize reducing these T gates, which even though they're single qubit gates are now expensive, and 2 qubit gates are still important to get rid of. And here, like, we're just looking at objectives that are very simple in counting the number of gates. You might want to also consider an objective like minimizing the depth, because like the longer your computation runs, the longer your qubits have to stay in the state that you've prepared them in, and that's something that they typically don't like to do. Great. So the high-level problem here is, given a circuit and some optimization objective, we want to output an equivalent circuit that minimizes. And this problem is in general hard. The result from this paper in particular is saying, like, given a circuit and a number of gates, does there exist a circuit, the decision problem of does there exist a circuit that is equivalent with like some like another number of gates that is hard, that's emphasized. So that in general, like you probably won't be able to have a procedure that is scalable and just like gives you the answer in one shot. So what you like to do is have these circuit transformations that are small, and you just apply them to subcircuits of your input circuit, and you do this process iteratively to shrink the circuit. And each of these transformations is going to preserve equivalence so that you know that the output circuit is equivalent to it. So at a high level, all an optimizer is in this setting, we're going to view it as like a set of optimizations along with a scheduling algorithm for applying these optimizations. And just to characterize the landscape a little bit, we're going to be separating these into both handcrafted solutions and ones that are more generic in the sense that like they're like synthesized. So like for a scheduling algorithm, what this would mean is like some generic search algorithm. And it's not really important, I guess, all these tools, what they do, but what they all have in common is that they all touch some portion of the handcrafted hemisphere. And so the question is, can we have a tool that is completely in this synthesized region? And I'll get into why you might want to have something like that later. And so this is the first portion of the talk. We're going to be mainly talking about how to synthesize a particular type of optimization. And then, like, once you have these optimizations that you can synthesize, like, what's the best way to apply them? Like, this beam search is kind of simple. And so some follow-up work tried using reinforcement learning to apply these optimizations. But then another distinction I want to draw here is like some of these optimizations you can synthesize them ahead of time, and then some of them you synthesize them at compile time. But this is like kind of something that like separates the existing tools. And so what if like, would it be a reasonable thing to do to combine these? And if you did, like how would you schedule them? And so that's like the focus of the second portion of this. And yeah, so first we'll start talking about queso, which will be about rewrite rules. So any questions up until this point? The rewrite rules, if you're familiar with classical compilers, are like probably the simplest thing that a compiler can do. There's this thing called peephole optimization, where you just have this like you have this collection of rules where they look like this. It's like a program, and you can rewrite it to the right-hand side, which is another program. And all you need to do is make sure that these are equivalent, and then that's it. That's a rewrite rule. And like you can have this like peephole or like this sliding window over your circuit to find matches of this left-hand side and just replace with your right-hand side. And so the important thing here is, what does it mean for two circuits to be equivalent? And as Abtin mentioned in the first part, circuits are just unitary matrices, and I don't think the definition was there, but this is what the definition is for a unitary matrix. And so checking if two circuits are equivalent is just as simple as checking if the unitaries are equivalent. And there's this like asterisk there because of this thing called global phase. So essentially, if I have this state that starts here, and I apply something that moves it over here, and I apply something else that moves it back to where it started, this like that's indistinguishable from doing nothing. So that's what we say is like equivalent up to global phase. And like mathematically, what that means is that your unitary is some like coefficient different from the other unitary. And this is a hard problem. It's hard even if you have a quantum computer. This complexity class QMA is like, you can think of it as the quantum analog of NP. But this is going to be an important thing to do if we want to synthesize rules. All right, so let's take a look at some examples of some simple rewrite rules. The first type are ones that you cancel out gates. And these are the best because they help our optimization objective directly. And it's pretty intuitive how maybe like the 2 X gates in a row would be equivalent to the identity. But in general, these rules are like kind of hard to derive and check if they're correct manually. And then there's another one where you can merge 2 rotations that are next to each other by just having a rotation by the sum of their angles. And then another important class of rules are ones that actually don't change the size of the circuit, but they move gates around. And this is important because in general, like you can't just do this and guarantee that you've preserved equivalence. So, and this is going to be important because also like if you couldn't move gates around, then all you could do was just apply these things that cancel gates out, then you don't have a very interesting search space for optimizing. And then lastly, there's this thing called for global phase, where if you have something that's equivalent to the identity up to global phase, then just get rid of it. And an important thing to note here is there are 2 things. One is that all of these rules have concrete gates in them. So remember, each device has its own native basis gate set. And so if my device is not over this set of gates, then what do I do? Like, how do I optimize that circuit? And the second thing I want to point out is that these circuits are symbolic. They are some of them are parameterized over these thetas, which are like angles that you're rotating. And so this rule holds for all values of theta. All right, so why is it a problem that they're concrete? Well, one is because this hardware box here is hiding a lot. It's not just one type of hardware. We have so many different types of quantum computing platforms, and new ones are cropping up semi-recently. I guess this is 2025. And each of these platforms, which have different ways of implementing a qubit physically, they also have different native basic gate sets. And for the same platform, as they improve it and they develop better gates, they can also change their native basic gate set. So for example, on IBM devices, when I started my PhD like 4 years ago, it was 1 gate set, and then it changed somewhere in the middle, and then it changed again. So you don't want to rewrite rules every time your gate set changes, or rewrite your compiler. So a natural thing to do is to use program synthesis to solve this, where the input to your synthesis problem is a description of some arbitrary gate set, and then the output is a set of provably correct rewrite rules. And so why is this hard? Well, let's look at just like a naive way of solving this problem, where we start with no rules, and then, oh yeah, there are some additional inputs, which is like the bounds on the size of the rules that you want to synthesize. So here it's like the number of qubits and the number of gates. But let's just enumerate all the possible circuits using this gate set up to these bounds. And then because we're interested in pairs of circuits, because our rewrite rules have a left-hand and right-hand side, we have a nested loop. And then if they're equivalent, then let's add it to our set, and that would work. Except the problem is the set of circuits that you enumerate, even for relatively small bounds, is going to be gigantic. And then secondly, this verification task is going to be expensive, and especially because our circuits can be symbolic. And then lastly, that verification task is embedded in this nested for loop. So now we have like this quadratic explosion. So it's not looking good. And I won't be able to get into like the nitty-gritty details of our approach, but I'll try to give you intuition for how it works. So essentially, what we're going to do is take a symbolic circuit and then have a procedure for turning it into a polynomial that represents what that circuit does. And then why do we want a polynomial? It's so that we have a way that makes it easy to group polynomials into equivalence classes. So if you can do that for polynomials and the polynomials correspond to circuits, then you have a way to group circuits into equivalence classes easily. So the first part of this relies on this alternative view of quantum circuit semantics, which is different from the unitary view that we've been teaching you about. It's like it's called the path sum semantics for circuits, but we won't have time to get into that. But let's assume that we have a way of returning a circuit into a polynomial. Why is that good? It's good because it's very easy to check if two polynomials are identical with high probability guarantees. And because I think that this is like a cute lemma, I'll spend the time going over it. All right, so what is this? Our goal is, given these two polynomials over some variables that are complex numbers, we want to check if they're equivalent. So a very simple way to do this would be if I set some finite subset of the domain of my variables, and then I sample a value for each variable uniformly and independently. And then I just instantiate the polynomials and I evaluate them. And I check if they evaluate to the same value. And if they evaluate to different values, then we know for sure the polynomials are not equal. So what happens if they do evaluate to the same value? Well, the failure case is if they were not equivalent, then the probability that this happens is at most d over the size of the domain that you sample from, where d can be very small and r can be the size of r can be very large. So in practice, what this gives you is a nice way of checking if two polynomials are equivalent efficiently and with high probability answers. And what you can do is that you can fix a set of fix a set of values, and then that lets you essentially hash a circuit into a value, and then two circuits will hash the same value if they're equivalent. And then you have a data structure that's like a hash map from values to circuit equivalence classes. So concretely, how this changes our naive algorithm is that we just replace this second for loop by just inserting it into this data structure, the polynomial identity filter, and then that's all. And the theorem is that the probability of getting a wrong rewrite rule here is at most the size of the number of circuits squared times the probability of failure for one of these tests. And the reason why it's squared here is because we're implicitly performing the Cartesian product, but we're not actually doing that because we just have one. And then another nice thing that this framework gets you is a way to reason about symbolic circuits that are symbolic both in the angle theta, but also just as a circuit. So this S block here can be any circuit that satisfies some simple constraint on its semantics, but you can think of it as a wildcard that you can apply when you're searching for matches. And I think that's the end of the rewritable section. So yeah,
I
question.
have a question on the algorithm, the little algorithm sketch in the
Yes.
previous slide. So circuits is a list of well, not every, but up to your bound, every combination of circuits, and I suppose you interpret you're just putting them together or something. Is that
Yeah, so you can think of it as circuits of size 1, circuits of size 2.
Mm-hmm.
Yeah.
And now when you say you put it in that polynomial filter, what does that do? I thought so that's supposed to compare equivalence with some probability bound, right?
Yeah.
Are you trying to compare it to all the size 1 circuits?
Yeah, so you want to compare it to all the other ones. So what you're trying to do is if you think of it as so this data structure is a map from some value to an equivalence class of circuits. Sorry, so it's
Uh-huh.
a set of equivalent classes of circuits. And so, oh wait, sorry. That was wrong. It is what I said initially. Just from a value to a set of circuits. And so all the circuits in this set should have the same value, and that means that they're equivalent. So that's what this part is. And how you get the value is by instantiating the polynomial with some real numbers and then evaluating it.
And you have to and then you have to repeat that some number of times up to how much you feel like you want to be confident.
Yeah, so just to give you so to give you an example, like if you instantiate this formula, like if I have 10,000 circuits and they have degree 10 and I sample from the 64-bit integers, then the failure probability is like 10 to the minus 11. So pretty small. Yeah. And yeah, you can repeat it. Other questions? Yeah.
Is there any clear relation between the degree of the polynomial that represent a circuit and what it costs to identify the polynomial?
Sorry, if I'm understanding correctly, you're asking the cost of transforming it into a polynomial? Or
Yes, and so the degree of the polynomial.
oh yeah, the degree. Yeah, so the degree will be a factor of how many. It'll be proportional to how many gates are in your circuit, and so these circuits are going to be pretty small. Both in the maximum, I think, in our evaluation is like over 3 qubits and 6 gates, because you don't need them to be very big to be good when you're applying them in the way that we're using them. So yeah, actually the polynomial is like, it has an exponential number of terms in the number of qubits. So it's not like we've solved this really hard problem, this QMA complete problem. It's just
and it is exponential cost, but we deal with small circuit.
yeah, exactly. Yeah. So really the benefit here is that we're getting rid of this nested loop. Because that's expensive. Okay, if there are no other questions, I'm going to move on to this other type of optimization, which is different from rewrite rules, and we're going to call it circuit resynthesis. We'll see why. So before I said that there's no hope that we can have this procedure that just like given an input circuit, it gives you the answer. But it turns out that if your input circuit is small enough in the sense that it's over only a few qubits, then this is tractable and you can use this procedure called unitary synthesis. And what is unitary synthesis? Unitary synthesis is just a synthesis algorithm where the input is a unitary and the output is a circuit that implements that unit. So this is a problem that is studied for like closely related, like different reasons. And a nice thing here is that you can approximate circuits because circuits are just these unitaries, so you can have a unitary that is approximately equivalent. So to illustrate this, if I have this input state and I apply a circuit to bring it over here, and then I start from the same place, I apply an approximation of that circuit, I can quantify how different these are. And by doing that, you can say, okay, well, if the distance is less than or equal to some epsilon, then we'll say these circuits are epsilon. So if epsilon is 0, then they're exactly equal. And one metric that you could use to compute this distance is something called the Hilbert-Schmidt distance. And people like it because it's easy to compute, and easy is in scare quotes because like this still requires you to have access to the unitary, which is exponentially large. And to give you some intuition on what this is computing, because these are unitaries, then U dagger, U prime, if they were equivalent, would be the identity. So if you take the trace and you square it, and the denominator is just like the dimension of the unitary squared. So if they're equal, then this value would be 0, and if they're not, then it would be 1. And it's nice because this satisfies our definition of equivalence, which was accounting for global phase as well. And if you want some physical interpretation of what this distance is, it's an upper bound on how far apart the probability distributions that these circuits are constructing are. And why would this be something that you want to do? So essentially, if I have no noise, if I have a perfect quantum computer and I execute a circuit on it, then what happened is I executed this unitary UC. But the reality is that our computers do have noise. And so the unitary that I've evolved my qubits by is not the same as the ideal one. So what if I approximate my input circuit, and let's say by doing this, I use k fewer gates. The hope is that the noisy execution of my approximated circuit is closer to the ideal than the noisy execution of the unapproximated one. And this could be the case if the noise from having those k extra gates is more than what I approximated by, which is epsilon. And I want to point out that even if you don't care about this part, then in full tolerant quantum computing, you need to approximate your circuit anyways because of reasons that we'll discuss later. But basically, you can't have arbitrary angle rotations. And so our unitary synthesis procedure just looks like this with this error epsilon parameter, and then the guarantee is that the output is epsilon equivalent. And like I mentioned, this is nice because it's a really rich research area with a lot of papers that try solving this unitary synthesis problem, and they come with these open source tools. And so even though people study this problem for a separate reason, it's nice that we can use their tools for circuit optimization. Okay, questions on synthesis? Yes.
Are there any like classical circuit optimizations that are at all useful in this setting?
Yeah, that's a good question. So actually this idea of like people optimizations and like resynthesis has been used to optimize Boolean circuit, like Boolean networks, these logic networks. So yeah, like there are similar ideas, but the semantics are very different. So it's difficult to directly apply. All right, so now we're going to talk about how we schedule these. And this problem is going to be hard because our set of circuit transformations is going to be pretty large if we include all of the rewrite rules that we've synthesized. And so the question is like, in what order should we apply these? And if you're familiar with classical compilers, this is a famous problem called the phase ordering problem, where it's difficult to determine a good order for applying our optimizations. And to complicate things, we seemingly have two very different techniques for doing this. One is like the rewrite rule paradigm, and the one is the one where we re-synthesize subcircuits. And they each have their own strengths. Like rewrite rules are very fast to apply because we pre-compute this database of patterns, and you're just searching for your circuit for matches. And resynthesis, you need to like compute the unitary and then send it off to the synthesis algorithm, which itself is like, like a pretty hard search problem to synthesize a circuit. So it's pretty slow. But rewrite rules are going to be limited by the size of the pattern that you're able to look for, which is like the number of gates. Whereas resynthesis is going to be more limited in the size of the unitary, which corresponds to the number of qubits, and is independent from the number of gates. So you could resynthesize a very deep subcircuit that only acts on like 3 qubits. And free rules are going to preserve exact equivalence, and even if you wanted to approximate, you wouldn't be able to because each of them are exactly equivalent. And then what resynthesis allows you to do is have this approximation back. And if we revisit our landscape here, none of the tools are really using both of these, except this like Hiskit and Tkit, which touches both the handcrafted and compiled time synthesized region, but they're applying these in a very like fixed course schedule. So is that the question is that really exploiting the synergy that these two optimizations can have? So, and so what do we need to like apply these optimizations freely is like a way of abstracting what they do. So the abstraction is very simple. It's just like this circuit transformation where you are input a circuit and it gives you a circuit, and there's some guarantee on the distance between these two, which is parameterized by epsilon. So under this framework, a rewrite rule is very simple. You just instantiate the epsilon with 0 because they're exactly equivalent. And then for resynthesis, it like matches the signature exactly based on this. And so now you have this framework where both of these optimizations are the same. And so what can you do with that? Well, you can plug it into this very simple algorithm that picks a transformation randomly, and then it randomly chooses a subcircuit to apply it to, and then just sees if the result is better, and otherwise you should reject it with high probability. And this is like it's inspired by simulated annealing, but it's simpler than the actual simulated annealing algorithm. And there should be an asterisk on step 2 here, because if you sampled a rewrite rule, like you wouldn't actually want to randomly choose a subcircuit. You would want to look at the pattern in the rule that you sampled. But let's say I apply this algorithm to a circuit. You need to be careful about bounding the error from these resynthesis calls, especially if they overlap. So in prior work that used resynthesis, they couldn't do a lot because their proof was on how the error accumulated was relied on the subcircuits being disjoint, and it was an additive bound. But it turns out that the same bound holds even if they overlap. So this is crucial because it allows you to just like apply this transformation wherever you want. All right. Any questions on that section? If not, I'll just have some comments on optimizing for fault-tolerant quantum computers. So the setting here, as I alluded to earlier, is a little bit different because our gate set must be discrete. So you see that none of these gates involve like a rotation by some angle. And originally, these T gates are expensive because we can't just execute them directly. We need to have this procedure for preparing this magic state that will help us execute this gate in a fault-tolerant manner. And you might be wondering, oh, like, why don't we just use a different gate? The T gate is not good. But there's this theorem that says that basically you need to have at least one gate that's going to be hard to do in an error-corrected fashion. And then also these 2-qubit gates, the C-naughts are going to be they're going to be expensive for a different reason. Not nearly as expensive as a T-gate, but Abtin's going to talk about in the second part how they can introduce some conflicts. But we have all these optimizers that I put in my landscape, and it turns out that none of them are like particularly stellar at reducing T-gates. And so it's an open research question on like what a good optimizer would look like for a tolerant regime. And there's some progress towards this with these domain-specific optimizers that only focus on reducing T-count. But even this like matter of what is the right optimization objective for fault-tolerant quantum computing is kind of open as well, because like over the years, people have come up with cheaper and cheaper ways of doing this distillation protocol. And so it gets to a point where like maybe that's not the cost that is dominating. And so yeah, that's all I really have to say about it. It's just it's very rapidly evolving according to all the work that people lower in the stack are doing, like coming up with better codes, better protocols for implementing the skates, and yeah, it's an exciting research area. Any questions on circuit optimization? Yes.
And maybe another question, which is, I heard that there's another kind of optimization one can do where if you are doing like a control operation or some multi-qubit operation, and like you're doing on very far qubits, and in certain implementations, they really do have to be close to apply those gates. So you have to just swap it a bunch of times. You know, like the status quo and like
Yeah.
optimizing for that kind of.
Yeah. So what you're alluding to is like actually like the mapping and routing problems that Abtin will discuss in the next section. And yeah, you're right. Like the optimizer phase could account for those types of costs in its optimization objective. It's not something that we've explored yet, but we've always talked about doing it. It keeps coming up, so maybe we just should. But yeah, essentially, if you were to do that, then like these two phases of the compiler that we've presented as being separate would like kind of inform one another. So that's probably a reasonable thing to do. So yeah, in the next session, he's going to talk about what you need to do to actually execute these gates. Because even though it's in the native basis gate set, there are going to be hardware restrictions on what you can do. I mean,
Yeah, go ahead. All right, cool. Yeah, so this what Amanda alluded to is what we call the qubit mapping and routing phase of the compiler. So this is basically like a cartoon view of qubit mapping and routing, where our inputs here are a circuit plus some characterization of the connectivity that we have available on our hardware, and the goal of the compiler is to produce some valid scheduling of the instructions that can be executed in while satisfying these connectivity constraints, and we're trying to minimize some sort of cost here as well. So I'm going to talk about first one concrete instantiation of this type of problem for NISQ devices. Okay, so on our NISQ quantum computer, there's limited connectivity between the different qubits. So this is like a real IBM machine's connectivity graph, which is how we represent this limited connectivity. So each of these vertices are a physical qubit that we have available on our architecture, and then the edges represent pairs that we can perform two qubit gates between. They're physical coupling links on the device. And you can see it's a pretty sparse type of grid that we have here. So we might run into problems with this limited connectivity. So if we kind of zoom in the top left corner of our device here, suppose that we're interested in performing some C0 gate between qubits P1 and P3. Well, we can't because there's no edge between them. But we have a way around this, which is that we can insert swap gates. So swap gates, as the name suggests, basically swap two qubits. They take as input, these two states, and then as output, their positions have changed. So state 1 is now state 2, and 2 is now 1. And in fact, we can implement the swap gate as the sequence of 3 of the C0 gates that we're already familiar with. This is not like a mysterious thing. It's just it emerges from these 3 of these gates. I guess this is kind of like the swap trick. If you ever had to do like an interview, a coding problem, it's like the XOR. You want to XOR two things 2 times, they swap their values. Cool. So now this is what we can use in order to implement the operation that we're interested in. So we can't actually directly perform a CNOT between P1 and P3, but what we can do is first swap P2 and P3, so now that state is living on our qubit P2, and then perform our CNOT between these two adjacent qubits. So this is what we call the NIST mapping and routing problem. We have an architecture represented as a connectivity graph and some circuit that we'd like to execute. And then the goal of our compiler is to take this and produce some mapping from the qubits that appear in the circuit to the physical qubits that we have in the architecture. And typically a single static mapping is not enough. So like in this case, Q0 is connected to all of the other qubits, but there's no such qubit on the architecture. So we also include these inserted swap operations. This is this problem. And it's important that we solve this problem well in terms of the number of swap gates, minimizing the number of swap gates that we insert. So if we look at like a real hardware characterization of devices from IBM on the left and Google on the right, you can see that the error rate of 2 qubit gates is on the order of 10 to the minus 3. Kind of as Amanda alluded to earlier, 2 qubit gates are extremely expensive, and the swap decomposes into 3 2 qubit gates if we're using CNOTs. And so we're trying to minimize the number of swaps. It's really important in order to get useful computation out of the computer. And so this is a pretty well-studied problem. There's this huge spectrum of approaches. It turns out the problem is NP complete. It kind of maybe sounds like it. We're doing some sort of graph, minimizing something over a graph. So then you have to make trade-offs. On one side, you have these heuristic-based approaches that you'll find in industrial compilers that can scale to really large instances, but the solutions they generate may be very far from optimal, and you don't get any guarantees about it. You don't know how far you're away. And then on the other hand, there are these constraint-based approaches that can provide an optimal solution, or maybe optimal up to some precise restriction of the search space, but they eventually run into scaling issues. They can't handle these very large inputs. So this is the trade-off that you have to make. And so in particular, I'm going to be talking in detail about a constraint-based approach. It's some of our prior work, where we encode the qubit mapping and routing problem as an instance of maxset. This is one example of something that you could use. Other tools have used like SMT or integer linear programming, but we use maxset. So many of you may be familiar with SAT solving. Basically, the SAT problem is that we have some formula that we're interested in, like this one that's a A or B and not C, and we pass it to a SAT solver, and the SAT solver provides us with a satisfying assignment, which is just a setting of all the variables so that it evaluates the truth. So like in this case, we could potentially set A and B to true and C to false, and the entire formula will evaluate to true. So this is an NP-complete problem. It's like a famously NP-complete problem. But what makes it interesting is that there's actually something that we can actually solve in practice in a lot of cases. There's been like many years of engineering gone into building and algorithms, building effective SAT solvers. There's this competition that happens every year. So reducing things to SAT can be an effective way to solve NP-complete problems because we have really effective solvers for it. And so we use maxset, which is kind of like, it's the optimization version of the SAT problem. So you can express like costs on different solutions. So again, our costs are the number of swap gates in our case, using soft constraints. So like to a maxset solver, you also pass the same input that's like some formula. And additionally, you have these soft clauses. So these are things that assign costs to various formulas. So in this case, we have some costs associated with A and B. So we have these soft constraints that say not A and not B with costs 1 and 2. So B, for some reason, is more expensive here. So the maxset solver is going to produce something that is not only a satisfying assignment of our original formula, but it's the satisfying assignment of minimum cost. So in this case, if you think about it for a little bit, you might notice that we only have to set one of A or B, so we should pick A, which is the cheaper one, and then we have to set not C. So this is the minimum cost satisfying assignment that has this cost of 1. So this is the framework that we're going to be using to express this NIST qubit mapping and routing problem. And here's how the encoding works. We use 2 sets of Boolean variables. On one hand, we have these map variables. Let's say like map QPT says the logical qubit Q is mapped to physical qubit P at time step T. These are just ordinary Boolean variables. I'm using this functional notation because the subscripts will be hard to read, but it's just Boolean variables. And then we have another set that says, okay, we applied this swap operation along this edge at this time step. And then using these variables, we can encode our constraints that say that the maps have to be injective functions. So each qubit in the circuit has to be mapped to exactly one qubit on the device, and you can't have collisions. And then the 2 qubit gates need to actually be executable. So if we're trying to execute a 2 qubit gate at some time step, then its qubits need to be mapped to adjacent vertices. And then the swap dictate how we transform the map. So when we want to change our map, we need to set some swap variable to true. And then finally, we encode the optimization objective as by paying a cost of 1 for each swap variable that is set to true. Okay. This first part, maps are injective functions. You have sort of this pair of dual formulas, one that says the injective part, that you can't have 2 qubits that are mapped to the same physical qubit, and one that says the function part, you can't map your same logical qubit to 2 different physical. And then this 2 qubit gates are executable. Basically, is like it's big disjunction of the edges. One of the edges needs to work for executing our gate is basically what this says. And then finally, we have this most complicated part that I wanted to highlight, which is that the swaps and the maps need to agree. So basically, we have a bunch of these swap variables plus this additional one that's like a no-op. It doesn't change anything, and we have to choose that exactly one of them, and then the one that we choose dictates how the map changes. So if we've chosen a particular swap, then the change in our map needs to agree according to this permutation that we associate with the edge, where the permutation is very simple. It's just swapping the things that are on the edge. P1 goes to P2, P2 goes to P1, and everybody else has to remain unchanged. So that's what we're denoting here is the effect of the swap on the mapping. And then finally, like I mentioned, we're associating a cost of 1 for each swap variable. So these are the soft clauses, are just single variable clauses, assigning a cost of 1 to everything except for our trivial swap that's not actually swapping anything. Any questions about this? I kind of went a little quick through that encoding, but yeah.
Is there no cost, or what would it be relevant to introduce a cost for swaps on that involve same wires? I mean, intuitively, I'm not sure how to think about it. Intuitively, it feels like having 2 consecutive swaps is worse than having 2 sequential swaps, because I don't think probability will, because on one hand you're adding to probability that you're multiplying.
Yeah, so it depends. Actually, it's typically worse to have a deeper circuit corresponding to consecutive ones, because our qubit lifetimes are so short. So a deeper circuit is going to take longer to execute, and so that introduces some probability there. So yeah, there are all sorts. You could also, so here we're optimizing for swap count, but there are other tools, and you can modify our encoding to focus on the depth of and minimizing the depth of your circuit.
I see. So optimizing for swap is like good enough.
Yeah, so it's a reasonable choice because of because the 2 qubit gates are so error prone. It's like some addition. It dominates over like the additional idling time, but they're like, if you wanted the full. It's a messy picture of like physical dynamics. Who knows what the cost is? But yeah, it's like an approximation. Good question. Anything else? Okay. So the problem with this approach is that we're solving an incomplete problem, so it's ultimately not going to scale to very large instances using this constraint-based approach. So in particular here, the search space of solutions is growing exponentially with the number of 2 qubit gates. So we have to reconcile that somehow, and we take sort of a local view of the mapping and routing problem in order to scale a little bit better. So what does that mean? So the idea is to solve mapping and routing as a sequence of subproblems that at the end will stitch together. So given this relatively large circuit, if we want to solve mapping and routing for it, we split it up into these subcircuits. And then so we begin with the first one and we encode it into a max-out problem as I showed above. And then we'll get some solution for the mapping and routing problem for this subcircuit. And additionally, from that satisfying assignment, we can extract like a final configuration of our qubits where they're mapped to at the end of executing these gates. And so we pass that on to the next section as an additional constraint that says you have to start from where we left off with mapping the previous subcircuit. And so here too, we'll get some solution for this subcircuit and we move along like this. And then eventually we might run into a case where we're unable to find a mapping and routing solution given these additional constraints. So then we sort of go do a little bit of backtracking. We say, okay, find me a new solution to the previous thing. So we pass back that initial configuration that you gave me and then say, don't give me this one, find a different solution. And then we can proceed now and say, now we find some solution for the third subcircuit, and then we continue along. And now we have solutions for each of these subcircuits. And because we're sort of passing these constraints between them, we can get a valid solution by just stitching them together. So now this is how we kind of control the growth and the size of the problem is by doing this sort of slicing procedure. Okay, so that's the NISP problem. I will pause here if there are questions.
Is it possible to rename?
Talk about now a different qubit mapping and routing problem. Okay, so we've seen this information before. Quantum error correction is the idea that you can encode one logical qubit with many physical qubits, and that will reduce your error, and the bigger you make it, the smaller the error. And this is something that we need in order to do the really exciting quantum applications like Shor's algorithm and simulation of quantum systems. Okay, and so the question is, how do we actually perform operations on these encoded qubits? It's a little bit complicated, but it has a nice sort of geometric flavor to it. It turns out that we can sort of merge and split these patches together. And the way that we perform a 2-qubit gate is by merging both of our qubits with a shared ancilla patch between them. So here we're executing a CNOT on these yellow logical qubits. And to do that, we allocate this path in the grid between them. Okay, so we can think about this as a graph problem as well, where we have we take our plane of qubits that represents our fault-tolerant quantum device, and we represent it as a grid graph where each of the vertices are a logical qubit, and then we include an edge between each pair of adjacent qubits. We get this grid graph, and so our goal here in the mapping and routing problem is to preserve the parallelism that exists in the circuit. So, for example, we have this circuit of two CNOT gates that we'd like to execute. So the first step is we need to find a mapping. We need to assign the qubits that appear in the circuit to patches that we actually have on our device. And then we need to plan the execution of our CNOT gates. So for each CNOT gate, we need to find one of these paths in the architecture. But the key constraint is that these paths are not allowed to cross. Once I've allocated this space for one of the CNOTs, I can't simultaneously use it for a different CNOT. So in this case, we're kind of blocked. There's no way to connect the two vertices that we'd like to connect. So we have to wait until the next time step, and now we've executed both of our gates. On the other hand, if we had chosen to arrange our qubits in a slightly different way, there does exist some sort of single step execution of our circuit. So our goal is to find a way to map our qubits and to route our gates so that we avoid kind of this serialization where we add extra time steps to our execution. So we're trying to find the minimum time step execution of our circuit. So this is a problem that we tackle in a tool called DASCOT, which breaks this up into two different phases. So in one phase, we have this mapping where we're trying to decide where to put the physical qubit, or to put the qubits on our device. And we do this in kind of a dependency-aware way, trying to predict which pairs of gates are likely to conflict. And then we have separately a routing phase. Once we've decided on the mapping, how do we route the 2 qubit gates, and we sort of search the space of possible orders in which to route gates, which we find is better than fixed heuristics that try to come up with some order in which to route the gates. And both of these searches at the mapping and routing phase are implemented using simulated annealing. So that's our approach for that. And we also have a baseline that encodes the surface code mapping and routing problem into SAT. So given some circuit and architecture and number of time steps k, it produces a formula that's true if and only if there exists such a solution. And so if the formula is satisfiable, we can get a solution out of that assignment. And if it's not, then we can just increment k and try again. And so in this way, we get something with the optimal number of time steps. So this encoding is very, very similar to the one I showed for the NIST case, but the most important difference is that we need to encode this no crossing between the paths constraint. So it's a little bit more complicated, which means that it doesn't scale quite as well. It's only feasible for tens of gates and qubits, which is what motivates kind of our simulated annealing based approach. So I'm not going to get into the details of this algorithm because you can see them later this week. Come on Saturday to the talk, and I'll sort of explain more about that there. Not here though. I'm ready to say. Okay, so we're doing cool. So we take a moment here to reflect. I've shown you 2 different qubit mapping and routing problems, and this one is a little bit different because now at the mapping phase, we're not so concerned with the distance between qubits because we just like the routes of any length take the same amount of time to execute. So the distance doesn't matter directly, though obviously there's higher chance of conflict if things are further apart because they're occupying more space. And then at the routing phase, we have this interesting situation where routing one gate can prevent the routing of the other. We didn't really have that in the NIST case. We could look at each gate and say, are you routable? Are you? But in the surface code case, now once we've chosen to route a gate, we sort of have prevented the routing of other parallel gates. And in the surface code case, we're not adding any additional gates like we were adding swap operations. We're just trying to minimize the time to execute, like the number of time steps that we need. Any questions on this part? In that case, I'll move on to the final thing, which is about our work in trying to unify these different flavors of qubit mapping and routing into a single specification language. So this portion of the talk is based on some work that has been just very recently conditionally accepted to POPL this year. So there's an archived version available now, and be on the lookout for the publication eventually. So let's look back at our picture of what qubit mapping and routing looks like. We have some sort of connectivity constraints that can change between different architectures, and some program we like to execute, and we're trying to produce the scheduling of the instruction. But we've seen 2 examples of this, and there are many more examples of qubit mapping and routing problems. So, for example, we might consider the case where some qubits are more reliable than others, or qubits that can physically move during execution. So devices that are based on neutral atoms or trapped ions, the qubits can be picked up and moved during your computation. So that changes mapping and routing, obviously. And then what if we have some sort of native basis set that includes more than gates over more than 2 qubits? And so these different variants of the qubit mapping and routing problem keep showing up. So based on this observation, we're trying to automate the process of solving qubit mapping and routing for a particular architecture. So the goal of our framework is to take some specification of the problem that describes the constraints of your architecture and pass that into our compiler generator, which will automatically produce a compiler for that particular qubit mapping and routing problem. So these components are this programming language we have called Merrill, and then this generic parametric solver with the max state solver. Okay, so let's look a little bit about how this might work. So here's another view of qubit mapping and routing, the NIST problem. So this is kind of the same instance I showed earlier, and then the same solution, but sort of represented in this tabular form. And what we might notice if we look at this is that we have some things that are general that apply to all sorts of different qubit mapping and routing problems, like this notion of a time step and a gate and an architecture that we'd like to target and a qubit map. And then these constraints that are basically, we have, our schedule is some coherent schedule for our circuit, so that like your steps of execution need to respect the dependencies that appear in the circuit, and then your maps need to be these injective functions. But what separates different problems are the answers to these two questions. Like, how do I implement a particular gate? So in the case of the NIST problem, it's like we need to find this an edge along which to execute it. So that's shown in blue there. And then how do I transition between time steps? Meaning, how can my mapping change over the course of my execution? So these are kind of the things that define a particular qubit mapping and routing problem. So the idea of our language, Merrill, is to facilitate describing the answers to those questions. So each of these blocks is going to be answering one of those questions. So the route info is the block for the first question. So we define this kind of construct this struct, the gate realization that has to appear in every one of these files that says, what is the data that is contained in an implementation of a gate. So since it's an edge, it has two architectural locations, which gates we'd like to route, and then this realize gate function, which basically tells us what are the possible realizations of my gate at a particular time step. So here, in order to execute a gate, I need to find an edge between the two qubits. So that's what this is saying. It's like the realizations are all of the edges that are between the mapping of qubit 0 and the mapping of qubit 1. There's only going to be one of those if you have a regular graph, but maybe you have some sort of hypergraph, I guess. And then so the transition info block is answering the question, how do you transition between states? So here, since our transitions are swap operations that you can insert, so they have kind of similar types of data. It's once again, it's an edge that we're swapping along, and then we define this function apply that says how our swap affects the map. So the punchline here is like, to get a solver for a particular qubit mapping and routing problem, I just need to sort of define these functions in this file. And then where this approach becomes exciting is that you can use it to answer slightly different questions really quickly. So what if you're interested in variability between different gate error rates? So on an actual device, it's not like every single 2-qubit gate is equally likely. It turns out, for some reason in the manufacturing process, this link is like 10% or 10 times even less reliable than other links that I have. This is something that shows up very common in the hardware. And so you can just sort of extend your file basically to account for this by adding some more data that contains the cost for each particular edge and modifying our cost function to access that cost to determine the cost for each of the swap operations. So we don't have to sort of construct a new solver, we just modify this file. Okay. So in the interest of time, I'm going to skip the algorithm that we have for solving these, but given a program, we have some algorithm to produce a solver for it. And I'm just going to sort of close with talking about the benefits of this sort of unified approach. And one of them is that we can sort of avoid duplicated work. So there's this work called Sabre that is very popular in the community that came up with this idea for finding mappings for the NIST problem. And what we've seen is that a lot of people, when they're working on a new set of constraints, they're sort of re-implementing Sabre for their problem. So the idea is that we can implement Sabre once in our generic framework, and then you can have it automatically for a new problem without having to re-implement it. And there's lots of other examples of like basically good ideas for qubit mapping and routing generically that we can implement once and then have available. And then the other thing you can do is sort of isolate the differences between problems, like what I was mentioning before. So we have this blocking condition that occurs in the surface code problem that we didn't really have in the NIST problem, that like you couldn't prevent one gate from executing by applying another, but here you can. And we can see this like as a program analysis over the program defining these problems. So by just doing some basic analysis of that AST, then we can see, oh, this problem has this different variety than the other one, and so we need to apply a slightly different algorithm that takes that into it. So this is another one of the benefits of like a unified approach like the one we have. Okay. So any questions about that section? Okay. Well then, at this point, let's reflect back upon this this view of the software stack that I showed you. Now we've talked kind of about these different stages of the compiler, and we have an open source tool that you can use to actually apply them. And so Amanda is going to give you a brief little tour of that. So,
Yes. So one slide quickly on the architecture of this tool. So essentially, it's taken a circuit in this format called Chasm, and then there's some additional parameters specifying the constraints of your architecture. So for example, you may want to specify the connectivity constraints or like the native basis gate set that you want to optimize over, or your optimization objective, or your error threshold if you're using the approximation from unitary synthesis. And then the internals of the optimizer are pretty simple. It's just the optimization phase, which is guac, followed by the mapping routing phase. And it's mediated by just another Chasm circuit in the middle. And if you're interested in running either of these, you can invoke them separately as well. And then there's plans to integrate these other solvers for mapping and routing instead of desktop. Great, and yeah, the output is the output from mapping and routing, which is no longer a circuit, it's more like a circuit that is scheduled throughout time. Great, and then now I'm going to do a live demo of installing our Python package and using it to optimize and route a very simple circuit. Okay, so did not plan for the screen to be over there. So yeah, we did the exact same tutorial in the previous session, so I already have a Python environment that has it installed, but just, I guess, to show you how easy it is, we can do that again. And we really recommend using UV for your Python virtual environment management. So yeah, let's create it with Sandbox too. And then we can activate it. And then it's really just as simple as install this, and then we have it. And because, yeah, I'll just switch back here. It's this like command line tool with, and yeah, and there are a lot of parameters. But if we wanted to, for example, optimize the circuit that we have, test circuit Python, we could invoke with the optimizer mode, which is somewhere in my history because I ran this 90 minutes ago. Yeah, so this command is just saying, I want to optimize the circuit, only run the optimization phase, don't trap and route it. I want my objective is to minimize 2 qubit gates. I'm going to set a timeout of 5 seconds because otherwise it'll run forever. And then I'll put the solution in this optimized .chasm file. And so it should run for roughly 5 seconds. Give or take. And great. So now we have this new file optimized.chasm. Let's see if it did anything this time. So our original circuit has 39 gates, and our optimized one. Oh no, it didn't this time. Oh, there. Previously it did. But I guess that's the beauty of live demos. Cool. Well, I'm not gonna run it for longer, but just trust me. Right, and then if I want to map and route the circuit that I've optimized, not really optimized because I did it for 5 seconds and I didn't change it. Then I run this command with the different mode. So this SCMR here just says like we're doing the surface code mapping and routing problem, and then output the solution in this JSON format. And it should be really fast because this is a pretty small circuit. So now we have this the schedule.json, which is a solution to the mapping and routing problem. And if you look at it, it's like not super readable, but it's okay because we have this tool that helps you visualize what the solution looks like. So I'm not gonna like add a new file here, but essentially you can step through the schedule and see at each time step like which gate is being routed and with like what is the path that is being used. And these end boxes here are for magic states for executing the T gates. But we didn't really talk about that in this tutorial. And yeah, that's pretty much it. Like if you have a different, if you want to specify a different type of architecture, you just change your architecture JSON. And like if we look at what that looks like, it's specifying like how the dimensions of this grid graph architecture, the locations that you're allowed to map your circuit qubits to, and then like the locations of these end boxes, which are magic state factories. And you might imagine for like different mapping running problems, this would look different. But yeah, that's about it. That's all we have, and we're right on time. But happy to take additional questions about anything that we talked about today. Yes.
So your REST tool takes in Plasm and spits out an optimized your assembly, is that right?
The optimization phase, yes.
Well, basically, I'm wondering if your optimizations could be went into a compiler for a higher level sort of quantum program language. I don't know if there's much work in that at the moment, but
Yeah.
it could be.
Yeah, that's a good point. Yeah. So actually, eventually that is a thing that we would like to do. But the thing is, these optimizations that we're synthesizing are over. It's relatively, I would say, easy to synthesize optimizations over these native basis gate sets. But what that looks like for a higher level language is probably very different. And so that's like a whole other research direction.
Okay, I just thought it could be useful to that sort of thing, but okay.
But yeah, that is definitely like the next thing because eventually we're going to need to have a compilation story from like an algorithm down to hardware. And you can do that now, but it's very open on like how should you express that algorithm? Like what language, what should a high level quantum language look like, and how do you compile? There are going to be optimizations, of course, at like the native basis gates that cannot express, but you can express it at like a higher level. So like how do you, yeah, it becomes very hard.
So you guys talked about a lot of different like sub problems in this space. Like, what if any of them do you think might be made like obsolete in, I don't know, say 10 years from now due to like hardware advancements?
Yeah, that's a good question. Well, we're always going to have some sort of mapping running problem. That perhaps the motivation for synthesizing rewrite rules given a target gate set, like it's once you move out of the NIST regime, it's like a little bit of a weaker story there because like we have a pretty well accepted gate set for fault tolerant computing. So maybe you could just like focus on what are the optimizations that you can do with that gate set. But even then, that's not, you can still do other things, so like. So it's probably still useful to build the sizes optimizations. Yeah, what else? I don't know, do you have
Hopefully
ideas?
the optimization objectives are constantly shifting as the architecture or as the hardware is improving and algorithms are improving as well for certain things. So I think fundamentally you have, I agree with what Amanda said, basically you have the same sort of steps, but like what you're actually trying to improve at each of those steps and what the constraints at each of those steps are, is changing.
I don't think. Yeah, the hardware will never be at the point where you don't need to do any of this anymore. At least I don't think so. Other question.
Just, I don't want to delay people, but I mean, custom is super high level compared to the hardware. Because let us say if you take the trap time one, you have the FPGA that controls the actual gate having very small number of microseconds before the decoherent, and they have to do that in one. That's IQ problems. If you go to the superconducting ones and IBM Google, then they have their own control problems. And then we also have the photonic ones, which talk about that separately, it's been confusing. So all of this gate optimization at this very super high level of custom, they kind of look okay from the PL perspective, but translating it as a hardware kind of changes as they try different things. Is something I'd like to talk to you about.
Okay.
It is because this is getting a bit weird. And look, I don't understand all of this either. I just have a very surface level understanding of this stuff.
Oh, yeah, for sure.
It comes down below that. I'm talking to physicists, so that makes sense rather than to the
Oh,
high
yeah.
level.
Yeah, there's a lot of, so if we go back to, I'm not gonna bring it back, but in our little stack, how hardware is at the bottom, like, that's hiding a
So this
lot
is
of,
why I also asked if you were going to go towards oracles.
oh, yeah,
Because things get a bit, let's just say confusing.
Yeah.
For the lack of that word.
yeah. The hardware box is hiding a lot, not only like different types of hardware, but like, once you get down to how these gates are actually implemented, they're like these waves, like they're these pulses, and you can further
There's no
optimize.
such thing as this is it.
Yeah.
That's not how it is.
Yeah,
And that's why
yeah,
this is very high level already.
yeah. But I guess compared to what we have in classical computing, it's low level.
That's what you like kind of like what? So
Yeah.
that's okay. Anyway.
All right. Well, thank you for coming. And yeah, if you want to chat more with us, we're gonna stick around.